Welcome to this video tutorial on the SUVAT equations. The SUVAT equations are 5 very powerful kinematic equations that can be used when the acceleration is constant. Let's start off by listing the variables we're going to be using. SUVAT is actually just an arrangement of the variables that we can use, where S is going to be the distance, U is going to be the initial speed, V is going to be the final speed, A is going to be the acceleration, and finally T is going to be the time. Note that we can also substitute in the vector equivalents of these variables, meaning that we can also have the displacement, the initial velocity, which goes for the one below 2, the final velocity. The acceleration has the same name for the vector, but we can put acceleration vector. And then time is always a scalar value. Each of the SUVAT equations is going to have 4 variables involved. It's going to have 3 known variables. So for example, in one question you might know the distance travelled, the initial speed, and the time it took, and then one unknown variable in which you will rearrange the SUVAT equation in order to make the unknown variable the subject, and then sub in your numbers, and you'll have the answer. Let's take a look at some of the equations. We'll start off with V equals U plus AT. As you can see in this equation, you have the final speed, the initial speed, and the acceleration and the time. Let's go on to the second equation. S is equal to U plus V in brackets multiplied by T, all divided by 2. The third equation, we have S is equal to ut plus 1/2 at squared. And then the fourth equation, we have v squared equals u squared plus 2as. These equations may look complicated, but they can be derived from each other. Here I have listed 4 of the 5 SUVAT equations. Therefore, we're going to use 2 of these equations to derive the next one. If you see, in this equation we have v, u, a and t, in this equation we have s, u, v and t, we can see that the equation that we're missing is the one that excludes u, because every one of these equations has u in. If there's 5 SUVAT equations, each with one unknown, then that means we can derive the equation that does not have u. So how are we going to do this? We need to make u the subject of 2 of the equations and then set them equal to each other to eliminate it. I'll show you what I mean. Firstly, let's take the top equation and rearrange it to make u the subject, which means make it so that u equals something. This means that we can rearrange this equation to get u is equal to v minus at. You can see I've just minused at from both sides, meaning that u now equals v minus at. I'm going to do the same with the one below. This is a little bit more complicated though. I'm just going to section off these. Firstly, I'm going to multiply both sides by 2, which will give me 2s equals u plus v multiplied by t. Then I'm going to divide both sides by t to give me 2s divided by t equals u plus v. We can get rid of the bracket now because there's no t to be multiplied. And then I'm going to minus v from both sides and switch around the equal sign, giving me that u is equal to 2s on t minus v. To make this clearer which equations we want, I'm just going to rub out the two intermediate steps. You can go back in the video if you want to see them. So how can we derive the final SUVAT equation from these two equations? As you can see, both this and this equal u. Therefore, if we know that u is equal to u, which it must be, we can also say that v minus at is equal to u, which is equal to 2s on t minus v. And then we can just remove the step in the middle, in which we can go back, and we can just say that this is equal to 2s on t minus v. Great. Now let's do some rearranging to get this in a slightly nicer form. Firstly, let's add v to both sides. This will give us 2v minus at is equal to 2s on t. Secondly, let's multiply both sides by t to get 2v t minus at squared equals 2s. And then let's divide everything by 2 and switch around the equal side, and we get s is equal to vt minus 1/2 at squared. And this right here is the final SUVAT equation. S is equal to Vt minus 1/2 At squared. Let's move on to a practical example. To the left of your screen, you can see some apparatus placed on the surface of a planet to drop a ball. This planet is the exoplanet TRAPPIST-1d. When the animation plays, the ball will drop, and we will be able to measure the time that it takes to fall. We're going to try and predict this ahead of time using a SUVAT equation. Let's get up the starting conditions. It has been given that s, or the distance travelled, is 3.6 meters. This will be the distance between the ball where it is currently and the ground. U, which is the initial speed, which is 0 meters per second as it starts from rest. And then the acceleration is going to be 0.69 g meters per second squared, where g is the acceleration due to gravity on the surface of the Earth. We should first of all note that in this example, downwards is the positive direction. We're doing this in scalars, but we could be doing it in vectors too. You'll see some examples of vectors later on. As you can see, we have 3 known variables, and I told you earlier that for a SUVAT equation we have 3 known variables and 1 unknown. We're going to try and predict the time at which the ball takes to reach the ground. So we should put a question mark here on the t, and I'll put a cross on the final speed, as we don't need to know it. We should also note that g for this question is going to be 9.8 meters per second squared, as the value for the acceleration on the exoplanet is only given to 2 significant figures. There's not really much point in having more than 2 significant figures for g, as we could not possibly know the extra information. So let's get started. We need to choose a SUVAT equation that ignores the final speed. Therefore, we choose s is equal to u t plus 1/2 AT squared. Now we want to try to find out the time taken to fall. So now we need to rearrange this equation for t, which is actually quite a task. Let's start off by multiplying both sides by 2. We get that 2s is equal to 2ut plus at squared. Now let's minus 2ut from both sides, and we get 2s minus 2ut equals at squared. Let's flip the direction of the equal sign and then divide both sides by a, and we get that t squared is equal to 2s on a minus 2ut on a. At this point we are lucky. Because the initial speed is 0 meters per second, it means that this term on the right will end up disappearing. Otherwise we would end up with a quadratic equation, which would have to be solved with the usual methods. However, as we are lucky, u is equal to 0, therefore this term will vanish. Therefore, I'm just going to say that t is the square root of 2s on a minus 2ut on a. Now let's sub in our values. This is going to be the square root of 2 multiplied by 3.6 divided by 0.69 multiplied by 9.8, and then minus 0 because our u value is equal to 0. This square root will give two values, a negative and a positive of the same number, where this number is 1.029, but obviously we only need the positive value as this is the only one that makes sense. As the question is entirely in two significant figures, then we can only, for certainty, write this as 1.0 seconds. Therefore, we have predicted that when we drop the ball, it will take 1 second to fall. Let's play the animation and see what happens. As you can see, the animation ended up being 1.0 seconds for fall time, which is pretty close to 1 second. If we knew our values more accurately, then we'll be able to more accurately predict it. Let's move on to some other examples. Firstly, a car is travelling at 10 meters per second in the direction of the x-axis. It has an acceleration of 2 meters per second squared in the opposite direction to the x-axis. What will the car's velocity be after 8 seconds? Let's start by writing out our SUVAT. S, U, V, A, and T. Considering we have been given an x-axis direction, we're actually going to do this as a vector problem, as it will make working with the directions easier. Firstly, the displacement. In this question we have no information about the displacement and don't wish to find it out, so we'll leave a cross. The initial velocity is 10 meters per second in the x direction, which means we had the direction x hat. The final velocity is the thing we wish to find out. We have the acceleration to be 2 meters per second squared in the opposite direction to the x-axis, meaning it's minus 2 x hat, and then we have a time period of 8 seconds. We have 3 known variables, one we wish to find out, so we use the SUVAT equation that does not use a displacement, which is going to be v equals u plus a t. Now we sub our values in. V is going to equal u, which is 10 x hat plus a, which is minus 2x hat, multiplied by t, which is 8. This will give us 10x hat minus 16x hat, meaning that our final velocity is minus 6x hat meters per second. This means that after the 8 seconds, the car will be travelling at 6 meters per second in the opposite direction to which it started. Let's move on to the second question. A dog is running towards its owner at a velocity of 4.5 a hat meters per second, where a hat is in the direction of an a-axis, which is arbitrary. The owner throws a ball, and the dog begins accelerating in the other direction with a magnitude of 1 meters per second squared. This would be in the negative a hat direction. If the dog begins at the origin, which is 0, or the null vector, meters, at what times will the dog be at the displacement 10 a hat meters? Let's write out our SUVAT with vectors. Firstly, the displacement. We are trying to find out when the dog is at the displacement 10 a hat meters. So 10 a hat is our value here. The dog is running towards its owner at the beginning at a velocity of 4.5 a hat meters per second. So that's our initial velocity. We do not care about the final velocity, so we can put a cross there. The acceleration we know is 1 meters per second squared in the opposite direction to the motion, which is the negative a hat direction, giving us a minus 1 or minus a hat acceleration. And then lastly, we have time, which we're trying to find out. Notice here that we have a, the acceleration vector, and a hat. They are not related. A hat is the direction, and a is the acceleration. Let's choose our SUVAT equation that ignores the final velocity, which will be s is equal to ut, where u is a vector, plus 1/2 a vector t squared. Let's sub our values in. 10 a hat is equal to 4.5 t a hat plus 1/2 multiplied by minus a hat multiplied by t squared. Let's simplify this out a little bit. We have 10 a hat is equal to 4.5 t a hat minus a hat t squared and 2. In fact, let's keep the a hats at the end of the number, giving us minus t squared a hat and 2. Let's take a new column and rearrange this to get all the variables on one side. We now get t squared a hat on 2 minus 4.5 t a hat plus 10 a hat equals 0. Now, as we know we're working entirely in the a hat direction, we can just ignore the fact that we have vectors and just work with the scalar values. Also, we're going to multiply both sides by 2. Notice that 0 times 2 is still 0. This will give us t squared minus 4.5, this will give us t squared minus 9 plus 20 is equal to 0. And there should be a t here. Now we solve this as a quadratic equation. We know that 20 can be made up of 4 times 5, and 9 can be made by -4 minus 5, meaning that we can factorize this to the following. If you do not understand this step, I would recommend looking up how to solve quadratic equations. This means that for this equation 2 equals 0, t could either equal 4 seconds or t could equal 5 seconds. And so we have answered the question. We were asked at what times will the dog be at 10 a hat meters for a displacement, and the answer is at 4 seconds or at 5 seconds. Thank you for watching this video tutorial. Visit my website coherentphysics.com for many examples with fully worked solutions.